Hi, welcome back. I thought we'd go over some of the concepts regarding momentum and impulse today and do a brief little video on some of these concepts, and we'll do a couple practice problems together that will hopefully help you solve your homework problems too. Let me share my screen. This chapter is focused on momentum and impulse concepts. So in everyday life, we use the word momentum very commonly, but in physics, it has a very specific meaning. Same thing with impulse, right? So we need to define these two terms using physics terminology. We're going to talk about the relationship between momentum and impulse. We're going to talk about why seatbelts, airbags, and other safety features on vehicles are there and the physics behind them. And we'll also talk about the concept of conservation of momentum. Okay. And lastly, we will discuss a couple of different types of collisions. What happens when objects collide and stick together versus what happens when objects bounce off of each other. So this chapter is concerned with the interaction between two objects and what happens while the objects are colliding, right? So you've probably seen videos like this before of car crash tests. You see this car didn't do very well in the car crash test. And we also down here below, we have a animation of someone that's in a car crash, and on the top we see them colliding with the airbag, and at the bottom we see the airbag doesn't deploy. Okay. And so what is the physics behind this? Why is it that she's safer when the airbag deploys? What does the airbag actually do? Because if she's moving along at, 50 miles per hour and she comes to a stop when she crashes, right? What's the difference between these two crashes, right? She starts at 50 miles per hour, she ends at 0 miles per hour, right? Her change in velocity is the same. So why is, a airbag safer than crashing into the steering wheel, right? We also have other examples of impulse and momentum in our everyday life, especially in terms of sports. Why do they tell you to follow through in your swing? Why is that important? And what is the physics behind that? And when you're shooting a firearm, right? Why is it important to hold the gun properly so that you don't have the gun recoil back and harm you, right? And what is the physics behind that? So there's a lot of very interesting applications to these concepts in chapter 7. And so I just want to go over them with you so that we, when we look around in our everyday life, we see these concepts all the time. So we're discussing now what happens during a collision, right? What happens when an object interacts with another object? When I drop a ball on the ground, what happens during the collision between the ball and the ground? Well, when the ball interacts with the ground, we know that there's forces, right? Newton's third law says that the force that the ball exerts on the ground is the same force that the ground exerts on the ball, except they're equal in opposite directions. And so what we're going to do is go back to Newton's law to analyze the collision, right? So what happens during the collision? What is the force that happens during the collision? So we're going to go back to F net equals ma, and we're going to look at the force that acts on the tennis ball as it collides with the ground, right? During that interaction between the tennis ball and the ground. Newton's second law tells us that the net force acting on an object is equal to its mass times its acceleration. We can rewrite this slightly to say that the acceleration of the object is equal to its change in velocity over change in time. That's the definition of acceleration, right? Change in velocity over change in time. So there's nothing really new here. This is still Newton's second law. We've just written it in a slightly different form. And the second line here, we've just multiplied both sides by the change in time. So we have the net force acting on the object multiplied by the change in time. This change in time would be like the time of impact between the ball and the ground. Okay. It might be the time of impact while your head is in contact with the airbag. Okay. So delta t here, this change in t, is the time of impact during the collision. F net is the force that acts on that object during the collision. That has to be equal to the mass of the object times its change in velocity. So this second equation is what we call the impulse momentum theorem. There's nothing really that new about it. It's still Newton's second law. It's just written in a slightly different way, and we typically use this equation to analyze situations where there's a collision happening. And we call the left-hand side of this equation impulse. It's the force acting on an object multiplied by the time of impact, right? It's the force over a certain amount of time. Its units are therefore going to be, it's a force times a time, so it's a Newton multiplied by a second. Those are its units for impulse. And notice that impulse is a vector because force is a vector. So impulse has both a size and a direction. The impulse acting on a tennis ball, if I drop it on the ground while it's in contact with the floor, the impulse is going to act upward because the force of the ground acting on the tennis ball is upward. The right-hand side of this equation is the change in the momentum of the object. We're going to define momentum in physics. In particular, we'll call it linear momentum because it's moving in a straight line. There's also angular momentum, which we'll talk about in the future. But linear momentum is when objects are moving in a straight line. And that momentum, we denote that with the letter P. Don't ask me why. We're running out of letters, right? But it's denoted with the letter P. And momentum in physics is the object's mass times its velocity. So that's our physics definition of momentum and impulse. The units for momentum, it's a mass times velocity, so it's going to be a kilogram multiplied by a meter per second. Those are the units. And again, linear momentum is also a vector quantity because velocity is a vector quantity. The impulse that acts on an object during a collision is going to be acting in the same direction as its change in momentum. So this right-hand side is equal to mass times change in velocity. I can rewrite this. Remember, change in this delta sign means change in velocity, and it's always the final velocity minus the initial velocity. So mass times the final velocity, that's going to be my final momentum. And mass times the initial velocity is the initial momentum. So this is our impulse momentum theorem. The impulse acting on the object is equal to its change in momentum. And this is the change in the momentum right before the collision and right after the collision takes place. So we might, think to ourselves, could a bowling ball and a tennis ball ever have the same momentum, right? Because the bowling ball is so much massive. Well, in reality, it could have the same momentum. If the tennis ball is moving fast enough, as shown here, if its mass is very small, right? But if it's moving fast enough, its momentum is 14 kilogram meter per second. If the bowling ball is moving very slowly, it has a large mass, its momentum, its mass times its velocity, is 14 kilogram meter per second. So theoretically, a tennis ball and a bowling ball could have the same momentum. In fact, the tennis ball could have even a larger momentum than the bowling ball if it's moving fast enough. Okay? So that's the idea behind momentum. You can see different situations. If a car is at rest, it's got 0 momentum. If it's moving at 10 meters per second, it has a little bit more. If it's moving at 20 meters per second, out of these 3 situations, it's going to have the most momentum. So momentum involves not only how fast the object is moving, but also the object's mass. And so when we look at a tennis ball, for example, that hits the ground and bounces back up again, right? If we think about what happens during the collision, right before the collision takes place, the momentum of the tennis ball is directly down, right? Because its initial mass times its initial velocity. Its initial velocity right before it has an impact with the floor is down. Right? It's moving down. There's an interaction that takes place between the tennis ball and the floor that's an impulse, right? The floor exerts a force on the tennis ball over a given amount of time. That creates an impulse acting on the tennis ball and a change in the tennis ball's momentum. And then after the collision takes place, the tennis ball is now moving upward. So its final momentum is upward. That's because its final velocity is also upward. And so if I wanted to determine the change in the tennis ball's momentum here, it's the final momentum minus the initial momentum. The final momentum is m times the final velocity, and it's pointing up. Right, so we'll write that here. The initial momentum of the ball was down. So we have to take that into account because remember, momentum is a vector, so we've got to take this direction into account. So I have the initial final momentum minus the initial momentum. The initial momentum is down, so let's put a negative sign for that. And since I have a double negative here, it's like adding. And this is showing that if the final speed and the initial speed are the same, right? If it's moving down at 10 meters per second and then it bounces back up at 10 meters per second, the final and the initial are the same. So I don't have to differentiate between them. And the change in momentum here is going to be, I just sum these up, 2 times mass of the tennis ball times its velocity. So the key thing with momentum and impulse is that they are vectors, so don't forget to take into account the sign or the direction of the momentum. So let's go into the thinking about why does an egg crack when I drop it on a hardwood floor versus why does an egg not crack if I drop it on a carpeted floor? In both cases, if I drop it from the same height, right, its initial velocity, let's just say I drop it from up here, right, at a certain height above the ground. And let's say I drop it on hardwood floor. And let's say over here, this is the carpet. Here's my egg. It doesn't crack when I hit the carpet. Okay, why? If I drop the egg from the same height, right, when it reaches the ground, it's going to have the same initial velocity right before it comes in contact with the ground, right? So there's an initial velocity here, an initial velocity here, and they're both the same, right? Because I'm dropping it from the same height, so it's not going to matter. And whenever it interacts with the carpet or whether it interacts with the hardwood, the final velocity of the egg after this interaction is 0. Right? It comes to stop, right? Whether it hits the hardwood floor or the carpet. So if I think about the change in the egg's momentum while it's interacting with the carpet or the hardwood floor, the change in the object's momentum is going to be the mass of the egg times the final velocity minus the initial velocity. Final velocity is 0. The initial velocity is acting down, so I'm going to put a negative sign here just to remind us. Final velocity is 0 minus the initial velocity is acting downward, so I'm going to make sure I put a minus sign there. So the change in the momentum of this egg, whether it hits the carpet or the hardwood, is equal to mass of the egg multiplied by its initial velocity. So the change in the momentum is not different for the egg that hits the hardwood versus the egg that hits the carpet. What is different? Right? Well, if we go back to the impulse momentum theorem, impulse is the force multiplied by sorry about that. Let me share my screen. All right. So if I go back to the impulse momentum theorem for both of these situations, I've got F delta T equals the change in momentum for the carpet and then for the hardwood. Right? Both of them have the same change in momentum, but what's different here? Okay, you might have already guessed it that the time of impact is different, right? For the carpet lengthens the time of impact. It's a cushion. Okay? So delta T for the carpet is very big compared to the hardwood. But if the change in momentum is the same for both the carpet and the hardwood, what does that tell me about the force? Well, the force must be very small for the carpet, and the force must be very big for the hardwood to keep these two things the same. So that makes sense, right? So the hardwood, you're going to have a very short time of impact, but a large force acting on the egg over that short given time period. On the other hand, the carpet is going to have a longer time of impact, and that reduces the amount of force that the egg feels, and that's why the egg doesn't crack. So that's what this little animation over here is showing. Impulse is equal to force times the time of impact. If you have more time of impact, cushioning, right, it's going to mean less force overall acting. So this is why we have safety features such as airbags in our vehicles, right? The change in momentum is the same. If I'm moving along at 65 miles per hour and I crash and my final velocity is 0 miles per hour, in both cases, the change in momentum is the same. But if I hit my head on the dashboard, versus if I hit my head on the airbag, there's a big difference in the amount of force I feel because the time of impact is different. The airbag lengthens my time of impact, meaning that there's less force acting on my head. Right? When I hit my head on the dashboard, it's a very short time of impact. The force is huge, and there's more chance for injury in that case. There's many other safety features that cars use. Crumple zones in your vehicles, right? The front of the car may crumple a lot, right? That extends your time of impact. The airbags, your seat belts, okay? All of those things are safety features that are true examples of the impulse momentum theorem. So let's do a little problem together. A golf club exerts an average force of 500 newtons on a golf ball that has a mass of 0.1 kilogram. The club is in contact with the ball for 1/100th of a second. What is the magnitude of the impulse delivered by the club? What is the change in velocity of the golf ball? Let's determine the impulse determined by the club. If you remember, impulse is the force acting on the golf ball multiplied by the time of impact, delta t. The force is 500 newtons that I'm exerting. Delta t is 1/100th of a second, so 0.0101 second. So if I multiply these together, I get 5, and the units for impulse, it's a newton multiplied by a second. This is why they tell you to follow through on your swing, right? Whether it's golf or tennis or whatever, right? If you're exerting a certain amount of force on the golf ball, right, whether it's 500 newtons or whatever, right, you want to exert that force for a large amount of time. Why? Because of the impulse momentum theorem. You want to get a large change in the object's momentum, right? So let's do that next. Let's figure out, what is the change in velocity of the golf ball? Let's apply the impulse momentum theorem. F delta t is equal to the mass of the, well, it's equal to the change in the momentum of the object. Delta p. Remember, p stands for momentum. And I'm going to write this slightly different. F delta t is equal to delta, change in momentum is the object's mass, remember, times the change in its velocity. This is the change in the golf ball's momentum. I've already solved for impulse, so I have the number that will go on the left side of my equation, and I know the mass of the golf ball is 0.1 kilogram. Delta V, let's think about what that's going to be. Final velocity minus the initial velocity. The final velocity is what we're looking for the change in the velocity, right? It starts out at 0 meters per second. It ends up at some final velocity, right, after I hit it. So the change in the velocity, v final minus v initial, is going to be F delta t, the impulse, divided by the mass. Divide both sides by mass. That's the change in the object in the golf ball's velocity. Impulse we just solved for was 5 Newton seconds. Mass of the golf ball is 0.1 kilogram. That has to be equal to the final minus the initial velocity. If I do this, Boy, that was not very clearly written, sorry. 0.1 kilogram. Okay, 5 divided by 0.1 becomes 50. If we're in standard units, got a Newton divided by a kilogram is going to be a meter per second squared, but then I have a second on the top, so it's going to be 50 meters per second. That's the change in the velocity of the golf ball. Right? So if the golf ball is just sitting there and its initial velocity is 0, its final velocity is going to be 50 meters per second. So again, this is why follow through is very important. I want to follow through. I want to give maximum time of impact while I'm swinging the club or I'm swinging the tennis racket, right? If I can increase the time of impact, I'm going to give it more impulse. And more impulse means a larger change in the object's velocity. The next part of this chapter is now focused on conservation of momentum. We've seen this word conservation before when we talked about conservation of energy principle. Conservation of momentum is a similar idea, and that conservation just means that it doesn't change, it stays constant. And in this case, it's the momentum that's going to stay constant before and after the collision. All right, so how do I know that? Well, let's think about it. Let's look at these two players. If I look at, I'll call this guy player 1 and player 2. Right? When they collide together, right, they're going to exert a force on each other. And Newton's third law says that the force that player 1 exerts on player 2 is the same size force that player 2 exerts on player 1, just opposite direction. For every action, there's an equal and opposite reaction, right? So the force acting on them is the same magnitude, and the time of impact is also the same for both players, right? So the time of impact is the same for both players. The force is the same, just opposite direction for both players. So this tells me that the force times delta t on player 1 has to be equal to the force multiplied by delta t for player 2. Now these two impulses, this is impulse, right? They're in opposite directions, so I'm going to put a negative sign here to make these two the same. So the impulse acting on player 1 is the same size impulse acting on player 2, just opposite direction. Impulse momentum theorem tells me that if the impulse is the same but opposite, that means that the change in momentum for both players is the same but opposite. So delta P, change in momentum for player 1, is equal to the change in momentum for player 2, just opposite direction. So we put a negative sign. I'm going to expand momentum out a little bit further on both sides. So delta P, change in momentum for player 1, is the mass of player 1 multiply the change in velocity for player 1. We'll do the same thing on the other side. And I'm going to expand out the change in velocity. So I'm going to have the final velocity for player 1 minus the initial velocity for player 1. It gets a little messy with the subscripts because we have to think about the two players and their initial and final momentum. So be verbose when you do this, write it out as explicitly as you can. The other side is going to be mass of player 2 multiplied by the change in velocity for player 2. Final velocity for player 2 minus the initial velocity for player 2. Now there's a little bit of algebra here in the next step, and you can check this on your own when you get a chance. But what I'm going to do is bring everything that involves initial velocity to one side of the equation and everything that involves final velocity to the other side of the equation. And what I'm going to end up with is m1 initial velocity for player 1 plus m2 initial velocity for player 2 equals, and then everything with final velocity on the other side. Mass 1 times final velocity for player 1 plus mass 2 final velocity for player 2. Notice that the left-hand side involves the mass times the initial velocity of each player. This is the initial momentum for player 1 plus the initial momentum for player 2. And this is the final momentum for the system for player 1 and for player 2. If I sum up their initial momentum for player 1 and player 2, that's the total initial momentum of the system of two players, right? And this is the final momentum on the right-hand side of the system of two players. What does this tell me? That the initial momentum of the players before they collide is equal to the final momentum of the players after they collide. This is what we mean by conservation of momentum. And this can help us solve problems. Like, what if two cars collide and stick together? How fast are they moving after they collision? Conservation of momentum says that the momentum of the system of the two objects, whether it's two players, two cars, whatever, right? The initial momentum of the system is equal to the final momentum of the system. Now, eventually, if these two players collide and stick together, eventually we know that they're going to slow down and stop, right? Because of other forces between their feet and the ground, for example, the frictional force there, right? But if the external forces acting on the system are zero, right, and the only force we're talking about is the internal force between the two players or between the two objects that are colliding, then the momentum will be conserved. And usually if we look at the collision like right before it and like right after the collision, it's going to be conserved. So when you see problems that involve things like collisions or stuff like that, think about using conservation of momentum principle to solve it. So let's work through this together using some mathematics. Let's suppose these two players are running towards each other, they collide, they stick together after the collision. Let's analyze the situation. What is the initial momentum of each player? Well, the initial momentum for player 1 is going to be the mass of player 1 times his initial velocity. His mass is 100 kilograms. His initial velocity before the collision is 5 meters per second, and it's to the right, so I'm going to keep that positive. So the initial momentum of player 1 is going to be 500. The units is going to be kilogram meter per second. For player 2, the initial momentum for player 2 is going to be the mass of player 2 times the initial velocity for player 2. His mass is 75 kilograms. He's moving at 4 meters per second to the left. Okay. So let's call to the left being negative velocity. So his initial momentum is negative 300 kilogram meter per second. The negative sign just telling me that his momentum is to the left. The total momentum of the system before they collide, right? So P initial, before they collide, is the initial momentum of each player summed up. So 500 kilogram meter per second plus negative 300 kilogram meter per second. That's going to be 200 kilogram meters per second. That is the initial momentum of the system of both players. Now remember, if momentum is conserved here, which it is, right before and right after the collision, the initial momentum of the system has to be equal to the final momentum of the system. So immediately after the collision, let's think about what happens. So we already said that the initial momentum before they collide was 200 kilogram meter per second. Final momentum must also be 200 kilogram meter per second due to conservation of momentum here. Well, we're not looking exactly for the final momentum of the two players. We're actually looking for their final velocity, right? How fast are they moving after the collision? So if I know that the final momentum is 200 kilogram meter per second, the final momentum is equal to the mass times their final velocity. Now, since they collide and stick together, right, their final, the mass after they collide and stick together is their total mass of player 1 plus the mass of player 2. And when they collide and stick together, they're both moving at the same final velocity, v final. So that's going to be their final momentum. So the final velocity, if I solve for that, divide both sides by the total mass. The final momentum is equal to the initial momentum. It's 200 kilogram meter per second divided by the total mass of the two players. Now, what was their mass? 100 kilograms and 75. If I plug that in, the final velocity is 1.1 meter per second. It's a positive value. That means their final velocity is to the right. Does that make sense physically? Let's go back and look at the problem. So this guy on the left is 100 kilograms, a lot of mass, and he's moving at 5 meters per second, high speed. The other guy is smaller. He's only 75 kilograms, and he's actually moving slower to the left at 4 meters per second. So he's not going to have as much momentum to the left as the other guy has moving to the right. So after they collide and stick together, it makes sense that their final velocity would be to the right because this guy is just going to overpower him. Right? So that's how you can always kind of go back and check, it physically makes sense. So that's how you can solve problems using conservation of momentum principle. This will work for cars colliding and stick together, however, whatever happens, like if they collide and stick together, it's easy to find their final velocity. Let's think about a slightly different application of conservation of momentum. And this is the example of what we would call recoil. So let's suppose I have two different skaters with different masses, larger mass on the left-hand side, smaller mass on the right. They push off from each other. Which one's going to gain the larger velocity? While they're pushing off from each other, they're going to exert forces on each other that are equal and opposite in size. That means their impulses are also going to be equal and opposite. And the change in momentum for each person is going to be equal and opposite. So the change in momentum for the larger person, I'll call it person 1, is going to be equal to the change in momentum for player 2, just opposite direction. So I put a negative sign here. They both start off with initial velocity of 0, right? And that they push off and they get some final velocity. So if I look at the change in momentum for player 1, it got a big mass here. I'm not trying to be mean, but bigger mass, right? And then change in momentum is mass times change in velocity. So final velocity minus initial velocity. And we already said the initial velocity was 0, right? Because they're starting from rest. On the other side, it's a smaller mass, right? In order to keep these balanced out on both sides, that means that the final velocity of the skater over here has to be bigger. So the less massive one is going to have a larger velocity in the end. This is exactly what happens when you shoot a firearm, right? When the bullet exits the gun, the bullet is, even though it's a very small mass, it's got a very large velocity, right? Now, there's going to be recoil. The gun is going to move backwards against your body, right? And even though the gun is more massive, it's still going to have a final velocity, right? And so, as you're holding the firearm, you have to hold it in such a way that you can control that final velocity so that it doesn't fly back into your face or harm other parts of your body. So that's the idea behind recoil. They move in opposite directions, and you need to make sure that, the example of a firearm, that you hold it properly so that you can control that final velocity. If the gun is free to move, it will recoil backwards with a momentum that is equal in magnitude to the momentum of the bullet, right? Bullet comes out, it has a momentum. The gun is also going to have a momentum in the opposite direction, same size. The recoil velocity of the gun is going to be smaller than the velocity of the bullet, but it can still be sizable, right? And enough to cause a jolt on your body and potentially harm you. So holding the gun properly is important. Go forward. Last part of this chapter is focused on the different types of collisions. And we've observed different types of collisions in our everyday life. These collisions are called elastic versus inelastic. The question is, when you have different types of collisions, is energy conserved and is momentum conserved? When the objects bounce off of each other, so it's shown over here on the right-hand side, the tennis ball just bounces right off the wall. We would call that an elastic collision. The best example of an elastic collision that I can think of in everyday life is when you're playing billiard balls. The billiard balls bounce off of each other and they don't stick together, they just bounce. That's called elastic collision. The other kind of collision is called inelastic collision, in which the objects end up sticking together. So the example of the two football players colliding and sticking together, that would be considered an inelastic collision. two cars collide. If they collide and kind of couple together and stick together after the collision, that would be called an inelastic collision. So an inelastic collision is one in which the objects stick together, they do not bounce. Energy is not conserved during an inelastic collision. However, momentum is conserved as long as there's no external forces acting on the cars. So for an inelastic collision, momentum is conserved, right? We can still apply conservation of energy, conservation of momentum. We did that for the football players, right? However, energy is not conserved during an inelastic collision. So if you calculated the initial kinetic energy of this railroad car and the final kinetic energy after the railroad car couples with these other ones, you would see that it's not the same, right? If I calculate kinetic energy initial before the collision and the final kinetic energy after the collision, it's not the same. Why is that? Well, the energy must be going somewhere, right? And in an inelastic collision, the energy goes into deforming of the object, right? Notice when this like clay substance like collides into the wall and sticks, it was deformed, right? Past the point of being able to go put back together, right? It's kind of like Humpty Dumpty. Like once you kind of deform it past a certain amount, it's not going to return back to its original form. It's past the point of being of going back to the way it was. So the energy goes into deforming the object, right? Cars crash together. The cars are deformed. They crumple. They don't just bounce off and like go back to the way they were before, right? They actually collide and crumple together. That crumpling is deforming. The energy went into deforming the objects. The energy might also have gone into heat energy. That's mostly where it goes, right? And that's what deforms the car. There might even be light or sound energy, right? Whenever the two cars collide and stick together. Right? So energy is not conserved for an inelastic collision because that collision, the objects, they don't bounce. They don't go back to their original form. It's not elastic, it's inelastic. They don't go back the way they were. So energy is lost there and we can't get it back. But we can still apply conservation of momentum here to solve problems. Elastic collision is the opposite. The objects bounce apart instead of sticking. We would call that an elastic collision. Energy is conserved, right? So if I calculate the kinetic energy before and after the collision, it would be the same. Momentum would also be conserved. The best example of that would be billiard balls. When the billiard balls bounce off of each other, there's no deforming there. They just bounce. It's elastic. It's like springy in a way. It's like boing, and then it goes back out again, and it doesn't deform the object. In real life, right, inelastic versus elastic collisions are two extremes, right? In real life, most collisions are somewhere in between, right? Maybe the cars bounce off of each other, but there is still some deforming of the car, right? So there's somewhere in between. Very rarely do you have a collision that's either completely one or the other. But for our purposes in this class, we'll just talk about either one or the other to make our life simple. Okay. That's all I wanted to discuss for this chapter. Like we did a couple of examples. We practiced impulse momentum theorem. We derived conservation of momentum, and we talked about the different types of collisions. So hopefully this gives you a good start to work through your homework problems. If you have any other questions on this material, please feel free to stop by my office hours or email me. Thanks.